So in part 3, we're going to make use of a property to solve exponential equations. And that property simply says that a to the x is equal to a to the y. So notice we have an equation this time. Then x is equal to y. So in other words, if the two bases are the same on your equation, then the exponents have to be equal. That seems pretty straightforward. So let's go do some. So example 5, we're going to solve each of these. We have 7 to the x is equal to 7 to the 3. So we're going to notice that both the bases are the same number. They're both 7s. So now I can set those exponents equal, and I'm done. So if 7 to the x is equal to 7 to the 3, then x equals 3. On part B, we have 2 to the negative x is equal to 2 to the 16. So again, the bases are the same. We're going to set those exponents equal and then solve. So we see that x is a negative 16. So not very exciting, and they do make some sense. Okay, part C is going to get a little more exciting. So here we have 8 raised to the negative x plus 14. And that's going to be equal to 16 to the x. Okay, well, this time, 8 and 16 are not the same base. Can I rewrite 16 as a base of 8? Well, no, because 8 to the first power is 8, and 8 squared is 64. And I skipped right over 16. Now, I agree that 16 divided by 2 is 8, but that's not what we're after. I have to write it as a base. I can't just come in and divide out things because each of these is involved with a base. You can't divide stuff out of here. So what we're going to do instead is take them both down to a base of 2 because I can rewrite 8 as 2 to the third power. And notice when I write that as 2 to the third, I then take what was there as the exponent and put it in a set of parentheses still up as an exponent. So I now have 3 times the existing exponent. On the other side, 2 to the fourth power is 16 multiplied by the x that's already there. Now that the bases are the same, we can set those exponents equal to each other. That's going to give me negative 3x plus 42 is equal to 4x. Or 42 is equal to 7x, or x, is equal to 6. So you can double check it by plugging it back in. You'll see that it works. Part D is a little more entertaining for me, at least. I don't know about you. We have 3 raised to the x raised to the third. So 3 to the x cubed is equal to 9 to the x. So 3 is already a prime number. I can't break it down any further, but we know that 9 is 3 squared. So for now, 3 to the x cubed is equal to 3 to the 2x. So there's the 3 squared times the x is already there. At this point, the bases are the same. We'll set those exponents equal. So x cubed is equal to 2x. And to solve that, because it is a polynomial, we're going to bring everything over and set it equal to 0. We can pull out an x. That'll leave me with x squared minus 2. So I'm going to get x is equal to 0. I'll get x squared equal to 2, or x is equal to plus or minus the square root of 2. So I get 3 answers, which is coming out of the polynomial part of this solving process. So 0, positive root 2, and negative root 2. Then there's one more example underneath this solving chunk. So part E asks us to solve 1/5 to the x is equal to 5. I'm going to go a little bit of a long way with this just because I want to use negative exponents any chance I get to get you more comfortable with them. So I'm going to rewrite this 1/5 as 5 to the negative x. I'm going to rewrite that 125. 1 over 125 is 125 to the negative 1. Now we need to make that 125 into a 5 cubed times negative 1. So 5 to the negative x is equal to 5 to the negative 3. So negative x is equal to negative 3, and x is equal to 3. So you could have gone a little bit quicker route with it. But again, I like using those negative exponents just to have you become a little more comfortable with them. So you're going to solve some equations. So first in the assignment, you're going to graph, then you're going to solve some equations. And then finally, at the very, very end, you're going to do some application problems. So example 6 shows you one place where you might see an exponential function. So example 6 is the atmospheric pressure P on a balloon or plane decreases with increasing height. So in other words, the higher up you go, the less outside air pressure there is on the balloon or the plane. This pressure is measured in millimeters of mercury. And it's related to the height in terms of P of H. So P for pressure, H for height. That's 760 E to the negative 0.145h. Okay, where h is the height in kilometers above sea level, and p is then the outside air pressure. So they want us to find the air pressure, find the atmospheric pressure at a height of 2 kilometers. So h is 2. So 2 kilometers, that's over a mile. So that's not too much, right? I mean, if you take a look at Pueblo, our elevation's already 4,000 something. So we're almost a mile high. Denver is a mile high. So what's the atmospheric pressure in Denver? So we're going to plug in 2. So we're finding P of 2. You're going to let your calculator do the work here. 760 to the negative 0.145 times 2. Make sure the negative 0.145 and multiplication of 2 is all up there in the exponent spot. You should get just a straight plug and chug 568.68. That's in millimeters of in millimeters of mercury, Hg. So not too bad. But what about where an airplane flies? So part B of that problem says, what's the pressure to height of 10 kilometers, which is 30,000 feet. So airplanes fly between 30 and 35,000 feet. So what's the air pressure up there? So 760 E to the negative 0.145 times 10. And if you do that, you should get 178.29. Again, it's in millimeters of mercury. So quite a bit less air pressure or atmospheric pressure. I keep calling it air pressure. It's atmospheric pressure. It's the pressure that's being pushed in on that airplane. So in order to maintain that, you have to have something pushing out. Right? So, then there's one more example. It's over in the social sciences, we call it. So our last example, example 7. Suppose that a student has 500 vocabulary words to learn. If the student learns 15 words after 5 minutes, the function L of t is equal to 500. Notice that that's the initial growth. So I didn't point that out over here, but over here at sea level, you could have figured out what the atmospheric pressure is by plugging in an H of 0, right? And then multiplying this out, you figure out what that is. So 500, 1 minus E to the negative 0.0061. So again, if I want to figure, we already know that the initial number of words to learn is 500. So if we plug in 0 up here, you get e to the negative 0, which is e to the 0, which is 1. 1 minus 1 gives me 0 times 500. In the beginning, they know none of them, which makes sense. Okay, but what after 30 minutes? So in other words, we've spent 30 minutes studying these vocabulary words. How many of them do we know? So we're going to plug in 30. So 500, 1 minus e to the negative 0.0061 times 30. So again, straight plug and chug on the calculator, and you should get 83.6 words. So in this case, I'm going to round down because we haven't mastered that 0.4 of a word. So we're going to say around 83. So after 30 minutes, we know 83 of the words that we have to know out of 500. So we need some more practicing. Then says, okay, what about after 60 minutes? So if we do 60 minutes of studying on these words. So L of 60 would be 500. 1 minus e to the negative 0.0061 times 60. And if you do that, you end up with 153.2. So we're going to call that 153 words. So we're still not anywhere close to our 500. We're still underneath the halfway mark after just an hour of studying those words. So it just gives you an example of where the E as a base pops into the real world. There are other bases, yes. Both the examples I could just happen to use. But they are plug and chug at this point. We can't solve for anything because we haven't learned our logarithms, which is in the next section. So I hope you enjoyed the exponential functions. I always find